Alright, I'm gonna show you today something I haven't found on YouTube yet, and it's super simple and super cheap. I think the cheapest possible way to control a stepper motor. You have maximum control directly from your computer. You don't need any controllers or anything. Your software is the controller directly. You can use your favorite flavor of programming language. I'm going to be using Labview because it's easy to visualize and show what's happening. So what's a stepper motor? It's a motor that has steps. So typically 1.8 degree steps, and by applying a pulse to it, it goes to the next step. So you always know where the position is, as long as you don't give it too much counter force, of course, because if you lock it, it doesn't do that. There's two windings, and you have to do something clever to make sure they turn left or right, counterclockwise, clockwise, extending, retracting. But typically you will use a motor driver, and it makes it super simple. You just have three inputs: enable standby, so does it work or not, move a step, and go left or right, clockwise, counterclockwise, extending, retracting, and all those things. And I'm going to be using this actuator, which you can also see in 3D printers such as the Prusa. So by rotating clockwise, it goes extending, counterclockwise, it retracts, or vice versa. It doesn't really matter. What is the normal way people now do it? Well, you have a proprietary controller in 3D printers, and you have to talk to it in a special language, like a G code or something, or you use Arduino and you control it directly. But there's a more direct way. Wouldn't it be better, instead of using the PC controller, driver, motor, to go and make the PC control the motor driver directly? So this is what I propose to do. We have a laptop or PC with your code. It talks to a UART, and that controls the motor driver and then the stepper motor. So this is a non-standard way of using a UART, really, but also very cheap, because these things cost like $3 or something. So how are we going to do this? Well, we're going to use a USB-to-UART device, the FT232RL. As I said before, you can get them from eBay and Amazon for $3 or something, and it emulates a serial port. And the output, even though I've now set 3V3, 3.3 volts, on the TX line I use 5 volts. What is TX? What is serial port? Well, a serial port is where you send the packet data. And this is what a packet looks like. You have a start bit, and then you send in 8 bits, and then a stop bit, and then that's one packet. And typically it will be at the 5 volt level. And if you have a 0, it goes to 0. And if you have a 1 for your digital data, it goes to 1. So just depending on data toggles. So for OXOO, 0, it would be this shape. And for OX33, ASCII number 3, for instance, it will be this shape, 1, 2, 3. And what I'm using it for is, if I send OXOO, basically that's one pulse I can send directly to the motor driver. If I send OX33, I can send 3 pulses directly to the motor driver. And you can come up with different pulse shapes with using your Windows calculator. And be sure to install the right drivers, etc. But you know, that's also details. Alright, but then I think, what about direction? We can send a pulse now in theory, but how can I make it go left or right, extending, retracting, all those things, right? So that's why I'm using this FT232RL. It has all these signals. It has DTR, it has DSR, DCD, RTS, RTR. These are all signals that historically have been used in secure communication with the receiver. Like you can ask, as a sender, you can ask the receiver, are you ready to send some data? Yes, I'm ready to receive some data. And these are inputs and outputs. So I'm repurposing one of these signals to control the direction to the motor driver. Super simple. And I will also be using another input later to detect when you're in a certain position. So zeroing is, right, okay, after you start up the system, you have no idea what position you're in, what state, what extension, what angle. So what 3D printers often do, for instance, or CNC machines or plotters, is they go to find a known position. So you keep driving until you hit a switch or an end stop, and then you say, okay, that's 0. And then with every pulse you apply, you just keep counting where you are. And if the forces countering are not too high, that works fine, that works perfectly. So typically we use a limit switch, and as I said before, I'm going to use an input on the FT232RL. So this is the schematic. It's super simple. Let me just walk you through it. So we've got the 3 signals: pulse, direction, and enable. All the pulse plus inputs, so these are optically isolated inputs, so they have a light, like a light diode or something in there to separate this electronics from this electronics. So I'm applying 5 volts to all the pluses, and if I pull this other one down, pulse minus, direction minus, enable minus, then I energize this input. So enable, if I pull it low, actually it will not be enabled, but so I have to have this high. Direction, if I pull this low, it can go, well, depending on how you wire the motor, left or right, extending, retracting. But you can, with a DTR signal, you can set the direction. And pulse, every time I pull this down for a certain time, it moves 1 pulse, 1 step. And then the limit switch, I pull up this CTS input with a 10K resistor. So when the switch is pressed, the CTS is low, and otherwise the switch is not pressed, CTS is high. And then finally, this is optionally, I can use other inputs to have more limit switches, maybe the other side of the axis, or keep track of, if I have multiple USB devices on my system, if this one is high and the other one is low, you can figure out, okay, this must be this axis because I'm pulling this high, and the other axis I'm pulling this low. So we have the PC laptop, the FT232RL, limit switch, power supply, which goes for this motor driver TB6600 from 9 to 40 volts DC. I'm using 24 volts. I'm setting the current to what this motor wants, which is now 2 amps maximum. And I've got a stepper motor, and it doesn't really matter how you wire them, because you can also always switch direction, or in software at least. But you have to make sure that the A windings and the B windings are correctly wired. And you can use your beep test on the multimeter to test which 2 wires belong to each other, because they will beep. So it's super simple. This is just how I wired it up. Right, how to control this thing. I'm using the free community version of Labview 2020 with an extra package NI VISA. VISA. This is to control the serial port. First I open the COM port. Then I say if the send pulse input is high, then this if statement is active. And it looks at the input DIRECT, direction extending. If it's high, then I apply the asserted state to DTR. If it's low, then I apply the unasserted state to DTR. So this sets direction. And then I send it a packet 0, which is the 1 pulse that I've shown you before. And I send this pulse to the VISA port. This gives it 1 step and sets the direction. This is just to keep track of what position you're in. So if I'm extending and this block is active, I put 1 on the output, and otherwise -1 on the output. Then I've got an enable block. If enable is high, then I unassert RTS. If it's low, I assert RTS. RTS is the pin to enable the motor driver, otherwise it'll be standby. And then I've got the CTS state, which is the switch state. If it is asserted, I say, okay, 0 position is achieved, the switch is active. And then I can detect which of the axes this is, which in this case I call it pillar A. DCD is asserted, okay, this must be pillar A because I'm pulling it up. using it in an actual program. So this block, I've put in this little block here, control stepper. I'm always enabling it, and then I have extend A and send pulse A, so this is the direction. This is sending a pulse. And then I've got some logic here. If the pillar A is not at a 0 position and a bunch of other things, then you can send a pulse. Or if the pillar A, so basically what I'm trying to say is, right, if I am in a 0 position, you cannot retract any further, because that will break the system. That will physically force the motor to contract and break the switch maybe. Of course, if you're zeroing, you can go to, when you're at 0, you can extend. That's fine. That's what we want to do. So basically, for the extend action, we're not zeroing. Zeroing is only in the very beginning. But if send pulse A is active and the direction is extending, then you can send a control signal. If you're not zeroing, and if you're not at the 0 position, and if you're retracting and sending a pulse, that's also allowed. 0 position is always detected. So this is a while loop. I should have explained this earlier. This is a while loop, detecting everything as fast as possible, maybe 1,000 times per second or so. This detects whether the 0 position has been achieved. The way I've programmed this, I think the Labview people will kind of scoff at me because it's a bit, basically I'm using global variables. So this controls an LED. So if this is asserted, it keeps this value open, and then it reads this value from here. So this is a separate bit from this and from this as well, but everything is linked together globally. So you cannot really control in which order things happening, but that is not really important for this example. Then there's a 0 pillar A function. This is a while loop as well. It goes and retracts the actuator until you hit the switch, and then it stops the while loop, and then it zeroes the pillar A position. Right, let me just show you how this, I'm finish the presentation first. No, I'll show you how it works first. So I've got this running here. I can extend, and then I can press 0, and look, position is now 16667. And it keeps going until the 0 position is achieved. And position is set to 0 again. So now if I want to retract, it doesn't work. But if I want to extend, that's allowed, and it counts position. So what I've shown you is it's super simple. You can directly use the USB to 232 controller to send pulses to a motor driver, which controls a stepper motor, and there's a limit switch, and that's basically it, really. Thanks for watching. If you have any questions, yeah, put it in the comments, and I'll try to keep an eye on it, really. And oh yeah, and the code, I've also put this story on hackaday.io. I'll put a link on there. It's part of my Solar Miller project, and yeah,